Hello to all of you. My name is Hidde. I'm a geophysics master student at Kiel University, and even though you can't see me, I would like to tell you a little bit about detecting very slow ground motion from radar satellite data over Schleswig Holstein and Hamburg. To begin with, let's have a closer look on the geological setting. The region is part of the North German Basin, the southern part of the Permian-Sechstein Sea. Today, this area is covered by hundreds or even thousands of meters of sediments, of which the uppermost layers are squeezed and superimposed by the glacial deposits during the last ice age. In this tectonically boring region, ground motion is a phenomenon that happens on a scale of only a few millimeters a year. Nonetheless, and as you already can see here, there's quite a lot of high-quality data on ground motion available, covering a period of time spanning from 1992 until now. This data was gathered by ESA satellites ERS-1 and 2 between 1992 and 2001, and by Sentinel-1 since 2014. But there are some serious things to consider when dealing with this data, especially when it comes to the older ERS data. Because for this region, older ERS data falls into three parts. An initial phase from 1992 to 1994, an acquisition gap until the end of 1995, and the rest. This results in often only weekly stationary data. We take care of this by recalculating those displacement rates that show a difference to the later part of the time series of more than one standard deviation. The result is not a new dataset, but a dataset with a little bit more accentuated structure. One can see this over the inner city of Hamburg, where the bluish points come a little bit better up. The second and bigger problem is the fact that data from different tracks, and to a certain extent from different satellites too, shows different characteristics. There are often offsets, ramps, making it hardly possible to compare those sets. Our solution to this is not to search for absolute movements, but to relate movements to the distribution of displacement rates. We don't look for a reference point, we look for a mean value and sigma classes. In the region where there isn't much ground motion, and this motion often happens only vertical, we accept the distribution's mean as a reference point 0, inherent to the data. This, in fact, is not a change, but for us it was some kind of a game changer, coloring displacement rates according to the displacement rates distribution allows to clearly see widespread movements as well as smaller structures. As you can see here, Hamburg on the left side in a raw data coloring, and on the right side in a coloring along classes of a half or 1 standard deviations around the mean value. With this, furthermore, we could identify the right-broken cavern in the southwest of Hamburg. And onto that, we clearly identify today the Elbe marshlands along the Elbe River, and as you can see in comparison to a soil type map, the distribution along the sigma classes nearly perfectly depicts the pink marshland soil along the river. An example for a smaller structure we found along the edges of the old historic town of Lübeck. There's a line of accelerated subsidence, and this line almost perfectly depicts an area of anthropogenic fields over pleat. This is one result. The other you'll find on the right side, and you perhaps want to take notice of that. Even though there is a shift between values from ES and from Sentinel data, both distributions nearly show the same shape. This is a phenomenon we often experience, and it helps us to compare data from different instruments, it is from different satellites and from different tracks too. A relatively new technique we are working with is the use of anthropogenic installations for calibration purposes. Our best bet at the moment are transmission towers on areas with strong hydrological influences, like the marshes. These towers are founded deeply to get rid of near-surface processes. Nobody wants to see high-voltage transmission towers tumbling forth and back. For a first test case, we used transmission towers along the Elbe River to calibrate displacement rates at Brunsbüttel. What was surprising for us is that there are areas sinking faster than the rest around, and in this case especially around the former nuclear plant of Brunsbüttel. To come to a conclusion, we can now say that PSIN's satellite displacement rates can be used to detect and measure even very slow ground motion processes. To do so, scales in terms of classes of standard deviations around the mean of a displacement rate distribution allows to see processes that do not show up when using linear scales. Where appropriate, installations like transmission towers with well-known displacement characteristics can be used to calibrate displacement rates. Okay, thank you very much for your attention. If there's something less, don't hesitate to contact me.